So we have one last research presentation for the day, and that is going to be from Shibaji Chakraborty. He's a PhD student down at Virginia Tech in the SuperDARN lab. So welcome, Shibaji.
Thanks, Nathaniel. Can you see my screen?
Yes, you just need to put it into presentation mode. Perfect.
Hello, everyone. I'm Shibaji from Virginia Tech. I work under the supervision of Dr. Ruhanami and Dr. Baker. And today I'm going to talk about the viability of nowcasting of solar flare driven radio blackouts using SuperDARN HF radars. And this study is deep rooted into the ionospheric physics, but I try to make it as simple and maybe as possible to access from a amateur radio point of view. Okay, so it all starts from the sun, which is the heart of our solar system. Sun emits electromagnetic radiation in all spectrum. It's almost a black body radiation pattern. So it radiates X-rays and UV spectrum, and sometimes it shoots out intensifies EM radiation in X-rays and UV, and that's commonly known as solar flares. And in this particular talk, we are only going to focus on solar flare impact on the Earth ionosphere and HF propagation. So here is the brief outline of my talk. First, I'm going to introduce the background of the study and the instrument, which is SuperDARN, I'm going to use. And second is like the how flare can affect the SuperDARN observation, some timing analysis and some algorithms, and maybe in the end, I'm going to talk about the SuperDARN as a solar flare monitor. And finally, I sum up everything what I'm going to talk about throughout this talk. So here is the a schematic diagram of the ionosphere and the propagating radio wave. So you can see the transmitter receiver curvature of the Earth, and transmitter sends out a signal, and it propagates through the ionosphere, and which is the ionosphere typically has three layers. We say like D region, E region, and F region. And sun shines on the day side of the ionosphere that creates this D and F region densities. And the HF radio waves is like propagating through this ionosphere, get refracted and bent by the electron density gradient in this D and F region. So ionosphere plays an important, you can see like it plays an important role in the radio wave propagation, and it's directly related to the amateur radio, ham radio, or even in the over the horizon radars and any other HF propagation. And ionosphere is highly variable and depends on different kinds of solar activities. And in this particular study, we're primarily going to focus on the solar flare effects on the ionosphere. Okay, so this thing is keep coming onto my screen. So the effects of solar flares are here is the effects is like it's called this sudden ionospheric disturbance. So what happens is like here is a schematic diagram. So it shows the sudden ionospheric disturbance. Here is the Earth. On the day side of the Earth, there is a transmitter receiver on the day side of the Earth, and here are the three layers I talked about, D, E, and F layer. And here is the sun, definitely not by scale, and it shoots out the enhanced EM radiation, and it creates an enhancement in the D and E region, and as well as in the F region. And that creates a sudden disturbance in the ionosphere, and which is called sudden ionospheric disturbance. And that's the first manifestation of this solar flare in terms of physical manifestation of solar flare in the ionosphere, and that creates two subsequent problem or issues in the traveling radio wave. First is known as short wave fade out, is the sudden increase in the radio wave absorption in the high frequency spectrum. And then the second one is sudden frequency deviation. So it's a sudden change in radio wave frequency that alters the phase path length in the traveling radio wave. To sum up all this thing, what happens is like sun shoots out some kind of radiative electromagnetic highly energetic radiation, and it intensifies the ionosphere, and somehow the radio wave which is propagating through that ionosphere first it gets absorbed, and sometimes it is the frequency of the radio waves alters. So these are the two different things that happening during following a solar flare, and they cumulatively known as sudden ionospheric disturbance. So why do we study this solar flare effect? So first thing is space weather. We want to mitigate the impact, or maybe forecast, or maybe somehow protect our instrument, or maybe we want a better propagation channel and communication link, which is directly related to the emergency management, amateur radios, aviation, defense, human life, etc. So I'll recommend you guys to go and read these two papers. One is Friesel and Redmond. They describe like 2017 solar flare, September solar flares that created some kind of problem in the during Hurricane Irma phase, when the amateur radio and emergency management system were evacuating people from the Caribbean island. So these two papers describe it really well. Why do we study these solar flare effects? The second is obviously space science. We improve our understanding of the fundamental processes, like I just talked about. It's sudden ionospheric disturbance, short wave fade out. What are the fundamental things and that is happening? And the most important thing I feel is like, it's a kind of why do we study, is like it is the fastest space weather manifestation of the solar flare. If you think about it, it's like a laser beam coming from the sun, and it creates an intense radiation which travels at a speed of light and reaches the earth. So it's the fastest possible space weather phenomena. So that's why we study. These are the study. I think I motivated you enough to do this study. And then so about the instrument, I'm going to use the SuperDARN, which is a super dual auroral radar network. On the left-hand side, right-hand side over here, it shows the northern hemisphere and southern hemisphere distribution of SuperDARN networks. So SuperDARN is an international HF radar network that probes the upper atmosphere. And you guys might know that HF propagation depends on refraction of the ionospheric electron density gradient. So the transmitted signal from the SuperDARN bends when it passes through the ionosphere. HF, and there are specifically two primary backscatter target. One is known as ionospheric scatter, and the second one is known as ground scatter. So ionospheric scatter, here is an example from the radar scan from the Blackstone radar. It shows the ionospheric scatter and the ground scatter, both of them. So ionospheric scatter is the scatter coming back from the ionospheric irregularities, whereas the ground scatter is the backscatter from the ground surface of the earth itself. So the lower corner figure is the illustration of how these two backscatter signals are formed. The ray, here is the radar, and here is the ground and ionosphere. So the ray passes through all three layers of the ionosphere and reflects from the F region irregularities and creates the ionospheric scatter. And it is also shown in this particular field of view plots, which is this velocity distribution, and then the ground scatter is shown over here, which is like refracted completely and bends back to the ground and it reflects from the grounds, and which is shown over here in the gray band of ground scatter. So the ground scatter is typically has a velocity which is mean absolutely near to the zero, because ground is not moving so much. So you can expect relatively less amount of velocity coming back from the ground scatter. And if you can imagine, like this particular one hop communication, it's like the ground scatter communication, ground scatter ground to ground link, which kind of replicates amateur radio link. So typically we are in the daytime, we are kind of dominated by this ground scatter signal. And for this particular study as well, we are going to use ground scatter data. So here is a flare impact on the radar. I'm using the data from the 5th May 2015. So here this radar fan plot or scan plot from Blackstone radar, starting from 22 UT, and all these scans are 4 minutes apart. So the gray band over here, it's the ground scatter. You can see a ground scatter, and you can see like the gray band converted just before flare started. It converted into a green band, which is like a sudden increase in the velocity. It's almost reaches out to the 100 meter per second, and then there is a complete bite out of the ground scatter band. There is no absence of ground scatter, and then it gradually recovers back to the pre-phase of shortwave fade out. So this absorption effect over here, it's the shortwave fade out, and this sudden enhancement in the frequency or the velocity, it's the frequency deviation, which is also known as Doppler flash. So here is another plot that is depicting the same thing from the same radar and on the same day. The top, this is the range time interval plot. The x-axis is time, y-axis is range, top panel is power, and the bottom panel is velocity. And you can see like here is a clear bite out effect, and this is the shortwave fade out absorption effect over here. And just before the absorption start, there is a sudden frequency deviation over here, which is also known as Doppler flare. So from now onwards, I'm going to only refer it as a Doppler flash. So you can think the Doppler flash is equal to the sudden frequency deviation and vice versa. So the timing analysis over here shown for that particular event, 5th May 2015 event. And the top panel shows the gauge flux. Panel B shows average power from the radar, Blackstone radar. The panel C shows the average number of ground scattered echoes, and the bottom panel shows the average velocity. So this red line passing through all these four channels, four panels are the starting of the solar flare. And on the top panel here, you can see like a sudden jump in the background radiation. That's the solar flare signature. And these two panels in the middle panel, you can clearly see there's a absorption bite out effect, which is the shortwave fade out effect. And finally, in the bottom panel, you can see this Doppler flare effect, where the velocity shoots out just before the absorption start. Now, to do the timing analysis, I'm just going to focus on the panel C. So I have developed an algorithm so that can estimate the different phases. So here is the onset. This red line given by this line is onset, which is the start of the absorption, and this black line is the start of the peak of HF absorption, when you can go completely in the blackout. Then this blue line is the start of the recovery, and finally this one is the ground scatter recovered ground scatter. So taking all this together is like you have three different phases, which is like onset, radio blackout, and gradual recovery. So some timing analysis. Here is the solar zenith angle effect on the timing analysis, and you can clearly see these are the mid-latitude SuperDARN radar. And on the top panel is the Blackstone, and then Fort Hays West, Blackstone from Virginia, Fort Hays West from Kansas, and then Christmas Valley West from the Oregon. And you can see there is a solar zenith angle effect. As you go closer to the sun, the effect is more severe. And then we did the timing analysis on the solar frequency. And you can see the solar zenith angle is kind of comparable in these two radar, but they're operating in two different frequencies, and the bite out effect is more severe where the radar is operating relatively low frequency. So finally, we compile all these things and produce a kind of movie, and it's a kind of SuperDARN space weather monitoring system, we call it. It's a distributed network of radar that is across the North American landmass. And we also pointed out the GOES satellite location, because we are also going to use some of the data from here. And the bottom panel over here is the time scale to show which time you are in, and the color scale on the radar only, it's like the green is known as the normal or pre-shortwave fade out, The red is the onset, the black is the blackout, blue is the recovery in under progress, and the yellow is data missing. So here is one. I'm going to show you a kind of retrospective movie of 1 hour in time, but I'm not going to run it for 1 hour. It might be for 30 minutes, 30 seconds or something. And this is the example where during September 2017 solar storm, it's an X8.9 class flare, which started at 15:30 UT on 10th of September, and the sun was on the east coast of the Northern America, which is over the Atlantic. And you can clearly see the progression of these four phases, like from green to red to black and blue. I skipped the black and blue because the movie is really long. So you can clearly see these 3 phase transition from green to red to black, and you can clearly see the progression from east to west phases. So I'm going to run. Okay. Yeah. So here is the onset. You can see the onset, and then it goes to blackout. And some of the radars did not receive the data properly. The algorithm is not able to detect it. So I'm again going to run it from the beginning. Oops. So here's the onset on the east coast, and then it propagates to the west coast, blackout on the east coast, and propagated to the west coast. Yeah, okay. So I'm going to move to the next. So yeah, here is my summary. So daytime SuperDARN ground scatter replicates a ground-to-ground communication link. So we can use that to replicate amateur radio kind of link, and it's also using the HF frequency, so it's susceptible to solar flare. Clearly, we can see a progression of different phase timings across different solar zenith angle, and these timings are also constrained by the transmitted frequency of the radar. And we produced a subnet, all the analysis, and we sum up with all the analysis and produced a subnetwork of SuperDARN HF radar that can be used as monitor SuperDARN solar flare using HF absorption across the North American sector right now. So thank you. Here if you have any question, you can email me or write. I don't know about the time. What is the time right now? I have times. So, and all the supplementary materials I uploaded to the folder. You can go ahead and check, and here are the published paper, which is talking about the analysis and the algorithm. Thank you.
Thank you so much, Shibaji. Really appreciate it. Carl and Francis, are there any questions?
There was one from Jonathan. He was wondering if the SID events correlate with detected SIDs using VLF transmitters.
Not really. Are you talking about the VLF, Stanford VLF
Yeah,
studies?
VLF.
Yeah, no, not really. They are not correlated with them, but I do read those papers.
Have you looked at that? Have you actually compared the data?
No, not really.
So you don't really know for sure.
This is Rich. I actually have that X8.9 on my thing for tomorrow. So it did correlate very well with what he just showed. And I have a super SIDS.
And so you have a poster tomorrow, right, Rich?
Right. It's on the first panel of my poster has that X8.9, that very flare that he showed there, and it shows up very beautifully.
That's great, Rich. Maybe you can put the link to your poster in the chat for everyone.
Okay.
Any other questions,
Nathaniel,
Francis? Oh yeah, Tamitha, go ahead.
Can you mind if I ask a question?
Go for it.
I have heard that, and this has been stated multiple times, that SuperDARN actually can detect a RF, basically a radio blackout, faster than the Space Weather Prediction Center ends up putting out alerts. And one of the things that the Space Weather Prediction Center does in the United States, they have a hole in their radio antenna network that basically skips out around 900 megahertz up past, I think it's around 900 megahertz up past like 1200. There's this hole where they don't cover any of that range at all. And I'm just curious, the problem that we have is the rapid adoption of ADS-B transponders and the fact that the FAA, as of January of this year, is requiring ADS-B out transponders they're mandated to be used on airlines, on all commercial airlines in the national airspace for the United States. Those transponders are going between 978 megahertz to 1070, exactly where this hole is that the Space Weather Prediction Center has in their ability to look at frequencies that could be, being impacted. Do you think do you think you guys could be a gap filler at all for the Space Weather Prediction Center in that case?
So what frequency are you talking about? 900 megahertz?
They're high. They're high. It's almost a gigahertz.
So we are actually running on 8 to 20. I'm not sure what filler you are talking about in terms of observing or monitoring the flare and its duration, definitely, but I'm not sure we are on the similar kind of frequency range. So
right, that's what I was afraid of. I didn't know if you guys had anything else, or if there was any other methodology that would allow that expansion. Just because they don't have any coverage, and as far as I know, there is no real-time coverage for that frequency range, and we're now very susceptible.
Okay, so here's the thing. I'm currently working on something which is relatively model basic, but that's the first principle based model, and that can be extended up to some frequencies. I'm not sure how it works for 1 gigahertz frequency, but it finds out what is the absorption at different frequency ranges, starting from 1 megahertz and beyond. I tested it up to 30 megahertz and some of the data sets with 5 megahertz or something, the Inoson data, but I'm not sure whether, but in terms of theory, it should work. So that's the thing.
Wait, yeah.
I agree with Shibaji. We could probably, SuperDARN could certainly see the SIDS, but to make a direct measurement at 900 megahertz, they're just not set up for that.
Or even have a model that would be reliable, that could be extrapolated.
That's an interesting question. Yeah, I mean, building a model for that might be worthwhile asking, but you should probably talk to Mike Rahanami tomorrow about that. So
okay.
All right. Well,
but
thank you
for this.
Yeah, thank you so much, Shibaji. That was wonderful.